Okay. Okay. Oh, I should have made it so I could draw on this. Oh well, rip. Okay, let's do that then. This first one's about percent composition, right? That's a thing from the first semester. I guess I should have. Oh well, rip. That's fine. So we'll talk about this because it might have been a while. Maybe you're already doing it, but let's see. So Z and I. 2. I want the percent composition of zinc. Right. Okay. So we got to be some things. So it's not too bad. Percent composition is, we want to figure out what mass of zinc. We want to figure out the mass of zinc over the mass of Cn by 2. Okay. All right, that's not too bad. So we need, first off, I need the molar mass of this guy. I need to know what the molar mass is. Right, and that's easy. We can do that. So zinc is 65. Well, I guess we also need the molar mass of zinc. Just 65.41 grams per mole. And then for iodine, we have 126.9. But I don't care. So 65.41 plus 2 times 126.9. So the molar mass of that I have my calculator ready to go. We get 319.21. Supposed to be a times 100 right here. So we do that, we got our 319.21 over my 65.41, 319.9. That's probably right. I probably rounded. I did. I think. Yeah, that's right. Yeah, 0.19. Yeah, okay. Okay, times 100. And before this is all wrong. 65.19.21 times 100. We get 20, essentially 20.49%. That's zinc's percent composition of zinc. Oh, you can't see it. Please let me share. Thank you. Right, so here it is. The tricky question is to buy this 33, right? Because maybe you think, oh, there's one zinc atom and 2 iodine atoms, so there's 1/3 of this is zinc, so don't fall for that. Okay. All right, there it is. Okay. This one's a limiting reactant problem. I don't think it's that necessary to talk about it personally. Let me know if you think otherwise. We'll come back to it. That's balancing the reaction. You can do that. Here's a good rate law review. Let's do this one, number 4. So we're determining rate law. We got our table. So we got rate is 4.02 times 10 to the negative 6. 8.04 times 10 to the negative 6. 1.13 times 10 to the negative 5. And we got lithium. We got 0.001, 0.002, and then 0.002. Lithium. We got nitrogen. We got 0.001, 0.001, 0.002. Right, and I want the rate law. Yeah. Okay. Here's that table. Right, I don't care about the reaction right now. Anyway, well, I don't care what it is because my exponents aren't determined by that. They're determined by this data. All right, let's see. Does anyone remember what we do with this? Nope, that's fine. Okay, so when we're looking in here, basically what we want is we want to pick spots where one of these changes and the other doesn't. Okay, so first, if I look at experiment 2 and 3, I see that lithium does not change, but my nitrogen does. So I'm gonna do 2, I'm gonna do 3/2. So 3/2. And then for my rate, that'd be for rate, that would be my 1.13 times 10 to the negative 5th over my 8.04 times 10 to the negative 6. And then I put that in my calculator, blah, blah, blah. And I get, to do that, I get, gross, why is it that 1.40, hold on, let me make sure I didn't write something down wrong. Nope, that's what it is. Okay, all right, that's what we're rolling with. Oh, this is okay. So and then for my N2, Did I do that right? 10 to the 1.13. 6. Okay, that's what we're rolling with. All right. Okay. So now if I do 0.002 over 0.001, right, 3 over 2, that's going to be 2. Okay, and then we're going to compare these two. So we're going to say 2, this one, to the what power x is equal to my 1.405. Because our goal, I guess I should have said this in the beginning, but our goal, we're trying to figure out that rate equals k times ln to, I guess I used x already, y to the n2 to the x, right? We're trying to find those exponents. So right here, since we're doing n2, we're finding our x. So I put x. 2 to the what is that? This is a little different because I think in class we only dealt with 0, 1, or 2, but one other case that is common is 1/2. And so I'm putting money on that's what x is. And if you didn't know that, what you could have just done is done your natural log of stuff. So if I take the natural log of both sides, yeah, and half. Yeah, you're right. Okay, x is a half. Good. You solve for it. Okay. 1/2. So I go up here, put 1/2. Okay. Do you think you guys can find lithium's exponent? Do the same thing, but instead find lithium. Right. Can you go over it? No. Yeah, that's fine. So now I'm looking for lithiums, and I need a place where lithium changes and nitrogen stays the same. So again, the first one, nitrogen doesn't change, and then lithium also, lithium changes this time. So we're going to do 3, 1. It doesn't really matter which one you do on the top. I'm just doing the bigger number, so I have to deal. Well, so I usually have to deal with whole numbers. So I'm going to do 2 over 1. Right, because I'm doing these two because lithium changes and nitrogen stays the same. So 2 over 1, I got the rate is my 8.04 times 10 to the negative 6 over 4.02 times 10 to the negative 6 negative. That's 2, I think. Someone let me know if that's not 2. For lithium, I got 0.002 over 0.001. So that's also 2. Again, 2, this one to the y equals 2. So my y is 1. Okay. There are my 2 exponents. And so this is my rate law. So I just go back and, well, just put 1. Go back over here, look at my thingy, wherever it is, somewhere. Please, tabs go away. This one, nope, that's different. Where'd it go? Here it is. I think this is it. That's the wrong one. Dang it, not that. Where'd it go? What the heck? Okay, there it is. So I'll choose this last one right here. Make sense? Remember this, doing this in chapter 14, I think? Yep, awesome. Is there, cool. Okay, this one, this 5, we didn't really talk about. Maybe you did in Gen Chem 1. So it's asking you about the difference between these two products. And basically this one, they're isomers of each other, which means they're the same, they have the same chemical composition. It's just one is arranged differently than the other, right? This one, this first one right here, you have the bromine, there we go, bromine in the middle. And on this one, you have the bromine on the end. So they're isomers of each other. Gonna be honest, have no idea why these two things are also right, but I'm pretty sure the answer to this one is all of the above. So I'm just gonna cut my losses on that one and say I have no idea why the second two are true. And I doubt, I'm a little doubting that he'll put a question on here, that there would be a question like this, since this is more on the organic chemistry side, and we didn't talk about that much. So we're gonna skip it. I guess we can talk a little bit about these two. Okay, look at those two. Also, feel free to stop me if you have questions about things. I guess I could just write, if you can see my little video thing, I'll just write this. So for the first one, it's asking you about the A thing, and it's talking about this. This is a little k. This is little. Can you see that? A little bit. Hopefully you can see my camera. Maybe you can. Let me know if you can't. I can't. That's fine. Here's a ridiculously large equation I'm writing for this A that's talking about what A is physically. There it is, ridiculously large. So it's asking about what this thing represents. I guess I could have just told you. So this thing is basically the maximum that K can be. This is the max of K, max of little k, right? The rate, this is a rate constant. The reason being is that this term is always, the max, this term is always less than or equal to 1, right? Because of that negative sign. It's always going to get smaller and smaller and smaller. Because all your activation energies are always, this is always positive. These two numbers are always positive. So this entire exponent's negative, making this always less than or equal to 1. So the biggest this can get is 1. So that makes K the max. Easy. Easy explanation right there. Or I guess you didn't really need the explanation. You just kind of needed the answer. And that's where I got the answer from. Oh, that makes sense. And then the other question is basically asking you about this thing, right? Remember this. This is our little, this is the state of the reaction. I guess you can think of reaction and this is energy, right? So this, they're just basically saying that they're asking you about this little bump, right? And a long time ago, remember, we defined this as our activation energy. Okay. So that's what they're saying. This this bottom little chart is what they're asking about. They're asking about this little bump. This is where our reactants hit each other. Those are the reactants getting ready to collide. And then the what does it say exactly? It says two reaction molecules meet and react, and the collective energy typically goes up and then down, as shown on the reaction type diagram. Yeah. So this up and then down. Cool. Oh, you can't see this. Here we go. Let's see. What else do I think is important? Oh, this is just writing the rate law for that reaction, or the rates, remember. Remember, so doing for this one, if we had N2H3, 3H2 plus 2NH3. So it's asking you about the, if we do this, remember we had rate equals the change in concentration of N2 over delta T, this one's negative, equals negative 1/3 delta H2 over delta T equals 1/2 delta of NH3 over delta T. Remember that? Right, this is just the coefficient. Those are the coefficients, right? This is 1/1 technically. And then the reactants are negative and the product is positive, right? Oh, there we go. Then from this, we see that the rate of consumption of N2 is equal to 1/3 the rate of consumption of H2. I think that was one of the answers. Go away. I'm not talking to you guys. I'm talking to stuff on my computer. Oh. What was the answer? It's this one. The rate of consumption of N2 equals 1/3 the rate of consumption of H2. So C. Double check myself. Yep. Everyone else good? Eugen's the only one talking. I just want to make sure I'm not. Okay, awesome. Here's the one yes. What else? What else? This one, these two. This one has to do with like some equation from chapter, whatever the EMS chapter was. I think it was 7, not 7. Yeah, 7 or 6, something in 6. I don't remember it. Gonna be honest, I'm not sure. It's this one's the answer. I'm not sure why it's not this one, but you know, that's fine. I don't want to waste your time trying to figure it out. This one also have no clue. Don't know what positron emission is. That's the answer. Not gonna talk about it because I have no idea, and don't want to waste your time. We can do some electron configuration though. That'd be nice. That's a good review. Okay. What's the ground state? So I wanted of S minus. So S minus is going to be, and then, so I'll do it for S first. So here we're looking for the electron configuration of an S minus ion. So do that, get a good review. So you would look at, looking at my periodic table, I see that a neutral, we'll do neutral sulfur first. Neutral sulfur has 16 electrons. 16 electrons. And I don't know if you remember, but our electron configurations we started filling different orbitals. So like 1s, had 2s, and then 2p, 3s, 3p, 3d, and then what, 4s, 4p. We don't need this much, but I think that's 4f. But whatever. So we had all these orbitals, and the way, this is how I remember it. I don't know how you, but the way we started filling them this way. You could also just look at your periodic table, and it's kind of set up in a way where if you just follow the rows and junk, it's already set up. So we got 16 electrons to put in places. So I got 1s, 1s2, so that's 2, 2s2, 4, 2p6, it's 10, 3s2, that's what, 12, and then 3p4. Right, or you could just look at your periodic table and you'll see that sulfur is in the third row, in the, not the fourth column, but the fourth column of the second tower or the tower on the right. So that's how you can kind of go ahead and jump and know that it's going to end up at 3p4, or you just count it, do it the way I did, doesn't matter. Then to get our S minus, surprise, surprise, this has one more electron, right? It's one more electron, so I just smack another electron into my highest orbital. So I go 1s2, 2s2, 2p6, 3s2, 3p5. There it is. Okay. Remember, we add and remove electrons from our highest orbital. So if it was S plus instead, right, S plus, would be 15 electrons. And so it'd be 1s2, 2s2, 2p6, 3s2, and 3p3. What else do I want to say about this? I guess they might, just in case, they'd ask you, they break it, or they write it different. This is the electronic, there's a noble gas shortcut. I don't know if you remember, but this is neon. So sometimes what people do is they just put brackets and then neon right here, and then the 3s2. So it'll look like neon, 3s2, 3p3. So if you do it this way for any element, it's the noble gas that comes before, like if you're following the rows this way and then going up, please. Okay. So this way and then up. So neon's the noble gas that comes before sulfur. So we'll put neon and then 3s2 and 3p3. Okay. All right. Don't know if you'll need that, but just in case. We didn't get answers or choices for that one, so exciting. This one's Vesper. I guess we can. Let's do that. Let's talk a little Vesper. Right, drawing things. Let's do Vesper. Vesper. Okay, so we're doing ozone. So 3 O's. Okay. Doing ozone. So there are 3 oxygens. So oxygen has 6. So what? There's 18 electrons, right? Yeah, 3 times 6 is 18. So not that bigger. 18 electrons. So right now I have these 4, so I have 12 left. Not 12, 14. Good math. 14. Okay. So I can start, all of them are oxygen, so I'm going to start putting them wherever I want. Okay. So that's what, 6? I'll put them on the outside ones first. 12, 14. Oh, you probably can't see these. Right, so that's my initial guess. This oxygen doesn't have 8 electrons around it, so I'm going to take one of these guys, make a double bond. And now everything has 8, so now I'm good with my octet roll. Okay, and so the thing about Vesper is the thing we're worried about is how many electron groups does a central atom have around it. So in this case, we have 1, 2, 3. That's how I count them. I draw little loops, and however many loops I have when I'm going around. Okay. But so I have three electron groups. So that means my electron group geometry is trigonal planar. Oh, that's not how you spell plane. Planar. But one of them is an electron. So my molecular group geometry is bent. Okay. So normally in my trigonal planar thing, so this, if it's just regular trigonal planar, the angle between all these is 120 degrees. But in this case, since we got a lone pair up here, this pushes these bonds downwards. So you get a less than. So this is going to be less than 120. Bam. There we go. That's the answer. Slightly less. There we go. Yeah, they're trying to get you with this about 120 because you would think if it's trigonal planar then it's 120, but we have a lone pair there, so it's going to make it less there. This one's naming. I think you can do that. Oh, I got a question. Oh, please. Why won't you? There it is. Can we do more practice problems on this, on drawing? Yeah, okay. Yeah, we can do that. Let me go. I guess I can just. Here, I know what I can do. I'm just gonna go get some molecules and we'll draw them. And then we'll identify their electron group geometry and stuff. Okay, where is that? Is it 8? Basic concepts. There we go. Sorry, give me a second. Hybridization. Oh, here we go. Cool. All right. Maybe it'd be helpful. So, okay. So, so let's do another one. Let's do. Oh, let's do. Let's not do that. Let's do. Oh, we'll do SO2. SO2. Okay, so drawing this, we want. So first thing I want to know is how many electrons does this thing have? Or valence electrons anyway. So if I look, both of them have 6 valence electrons. So there's 6 here, plus 2 times 6. So what's that, 18? Got 18 electrons total. So S and 0, 0. Okay, that's my guess. So I put my, which one's more electronegative? Oxygen. Oxygen's more electronegative. So I start putting my electrons on here. How many? That's 12, isn't it? Yeah. So I had, so it's 16. I need 2 more. So right there. Sorry, I went crazy there for a second. Anyway, okay. Hopefully you noticed again that sulfur has 6 around it, right? These 2, and then those 2 lone pairs, but we need 8. So I'm gonna make one of these lone pairs into a bond. All right. I guess you wouldn't really be. It doesn't really. So sulfur, we would check our formal charges here. And so we would see we got a -1 on oxygen and then a +1, I think. So I guess I should actually do it since I don't know. Okay, so for formal charge, it's the formal charge, Jesus, going crazy. Charge, it's going to be the number of valence electrons, number of valence electrons minus the number of bonded electrons, so valence electrons, minus or not the number of bonded, the number of bonds. I guess you could say 1/2. Let's do bonds. Number of bonds, I like this. Minus the number of number of lone pairs. That's what I wanted. Lone pair electrons. Losing my mind. Okay. Okay, so for sulfur, we had 6 valence, right? We get that from periodic table, minus how many bonds? 3. And then how many lone pairs? We have 2. Sulfur has a charge of +1. This, we'll call this oxygen 1 and this oxygen 2. So oxygen 1, so we have 6 valence electrons minus 2 bonds minus 4 lone pairs electron. So that's 0. And then my oxygen number 2 has 6 valence minus my 1 bond minus 6 the lone pair electrons is my -1. Okay, this is one of the weird cases. Sulfur is on row 3. So in when you're doing this, there are times when you have an element that's on row 3 or below that you can give it more than 8 electrons. Because usually we'd be happy with just this 8, but sulfur can expend its octet, if you remember that term, and can basically take in more than 8. So that's what we're going to do right here to decrease its formal charge. All right. So that was when the previous one we had. So that's this. So now if I draw it a new way, I draw like this: S dot 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 O S and then O. So now when I do formal charge for my S, it's going to be 6 minus, it has 4 bonds now, minus 2 lone pairs, so that's 0. And then oxygens are the same now, they look the same. And it's going to be 6 lone pairs minus 2 bonds minus 4. So 0 again. So that's the ideal. Okay. I guess you could have left it like that and wouldn't have changed what we're going to do now, but just in case they ask you to put the correct thing for that. Now we're safe. Now we're ready. Where did my blue marker go? This thing here. I lost it. Yeah. Anyway, all right. So now we do the part where we identify as Vesper. Great. So I look at this lone pair. Oh, it's going to be the same. I look at these. Right. 3 electron groups. 3 electron groups. So it's trigonal planar. For the electron group geometry, and then for one of them's a lone pair, so it's bent or angular for its molecular geometry. All that to get the same thing. So let's do we'll do that. Oh, we already did. Let's see, 3 maybe. No, let's do. We'll do Z and F4. I already saw this. So here's that. This is the molecular geometry. Right. We'll do another one that's different. Go over here. So I don't need this. It's my quick review of our formal charge. So we got, now let's do XEF4. So let's see, how many electrons, valence? I think xenon, which is XC, has 8. Yep, xenon has 8, fluorine has 4. So 8 and 4 times 7. What's that? 28, 36. All right, so hopefully someone's fact checking my math. Okay, xenon's probably going to go in the middle with F's flanking it. Okay, so how many? That's 8. that minus 8. So I got 28 left. Ooh, excuse me. We got 28. Yes, yeah, 28 left. So what is this? 6 right here. That has 8. 12. 18. 24. Okay, so I need 4 more. But these fluorines aren't, I can't expand the octet with my fluorines, so I put them on xenon because it is below the 3rd row of the periodic table, so I can expand it. Okay. Now here, let's see, let's look at our things. Okay, how many electron groups do we have? We have 1, 2, 3, 4, 5, 6. Right. So what I'm doing there is I'm just basically going around, and I have to go around all these bonds, like bonds and lone pairs I have to go around. So, and every time, so then I count up all the loops or bumps I have. So 1, 2, 3, 4, 5, 6. Okay. So 6 electron groups. I guess, here, let me do it. Electron group, I have 6. That means it is it octahedral? Ooh, I think it's octahedral. Yes. Octahedral. Okay, and then how many lone pairs do I have? 2 of them are lone pairs. So that means I think it's square planar. Yep, square planar. Square planar. Right. So basically if this does come up, it's gonna be something where it's like, hey, which one of these pictures is right, or what's the shape? Oh, and I guess I should have been talking about angles. So here on our octahedral thing, we had it's going to be, so here, this is weird. The angles. If the angles on this one, I think they're all still just 90 because so we had our octahedral looking thing. So look kind of like this. Right. With, this middle and the ends are atoms. Then this became a lone pair, and that became a lone pair. There's a lone pair right here, a lone pair up there, right there, above and below. And they're just kind of pushing on the, oh, you can barely, here, that bigger. So we have our big octahedral thingy, this way and that way. And then we have like a lone pairs, top and bottom. So one right there, one up here. And they're kind of just pushing, like these are 90 degrees respectively all around. And these are kind of pushing on all of these equally. It's just flat to keep them flat. Okay. The main thing to keep them flat. What else should I say? For Vesper, a lot of the things for Vesper is just this. There's a table on, I don't know, maybe you got, I don't know, that's how you spell the abbreviation, but on page, what is it? In my book, it's 375 on the 4th edition, just in case you have a different one. So it should be somewhere around there though. But oh, so would it be less than 90 degrees since the lone pairs are pushing them? Well, the lone pairs are going to be pushing them like flat, right? You have a lone pair on the bottom of this. Like if you had, so basically you have like a lone pair on each side, and they're both pushing this way. So they're not really gonna do anything. If I had another lone pair, so if one of these is a lone pair, right? Maybe I had a lone pair sitting over here as well. then it would be less than 90 right here. This would be less than 90. But do you see? Yeah. So since they're symmetrically on the pushing, then it's going to be still just 90. But once you get, if you get something like this, or maybe even this as well, then it's going to be less than 90. Here, maybe if we had, instead of adding lone pairs, we took one away. Get rid of these, get rid of this. Maybe we had something like this. Then this would be definitely less than 90 for all of these. But once you add in this lone pair and get kind of a symmetric push, yeah, I should be just 90. Anyway, what was I saying? This is where all the Vesper stuff, so it tells you if you have this many electron groups and however many lone pairs, it tells you what shape, right? Just so if you're, honestly, you probably won't want one of the smaller ones. I'm thinking it's not going to be, these questions should take not that long. And if anything, the answer is going to be blatantly obvious once you kind of know. Maybe even if you just knew what its electron group geometry was. So am I telling you to go and drop a marker? Am I telling you to go memorize a chart? No, I'm just saying maybe go look at it and kind of remind yourself on what all the things are. Maybe. But that would be good. A good idea. No problem. Let's see. Oh, I did have, so tomorrow, so I was thinking doing, well, I had a question. Would it be better for me to go from 7 to 9 instead of 8 to 10? Or is 8 to 10 at a good time for you guys? I'll probably send out a poll depending on how this goes right now. Because I don't want it to be too late. It doesn't matter to me. Cool. Same preferences. If I moved it, 8 is fine. 8 is good. Okay. I don't care. Okay. I might do a Google thing. I don't go to bed until like 5 a.m. Same, Eugen. Well, not 5 a.m. I'm usually, well, yeah, I have no idea. Anyway, okay. Okay. Yeah, I'll probably just make a Google poll. The reason I asked is one of my roommates wants to hang out at 9, and I told him I had SI. And it's like I might just push it forward. So we'll see. But yeah, so tomorrow, what am I gonna do tomorrow? Tomorrow I've been looking through all the worksheets and all his PowerPoints, so I'll probably just go through some of his well, I guess depending on when he does tomorrow. If he does one of the questions I want to do, I won't do it. But we'll just go through, I guess, all the chapters basically. Just do some problems. If you have any questions, if there are things you're particularly worried about, come and ask, because there's a good chance if I'm just left here talking, I'll probably skip it, unless I don't. But better to be safe than sorry. Geez, I have some friends that are going crazy in the group chat about Survivor, and I haven't seen it yet. So anyway, that's all I have. Is there? I guess we can. Yeah, we'll be done. Go through the worksheet's not too bad, right? Nothing too. Well, they're kind of. The reason it's a standardized test, they're basically trying to trick you with words instead of difficult problems. So if anything that's going to get you is probably the wording of something. Um, but now I'm just rambling. Is there anything else you guys had to questions, or did you want to talk about the worksheet more? Oh, can you put the link in here again? Yeah, there you go. Is it working? Yeah. If not, I can just sign you engineer. It's all fine. But yeah, unless you have anything you guys want to talk about, we can be done. Did I record this? I did. Good. Oh, did I put Sundays up? I don't think I even put Sundays up. But you're welcome. Yeah. So I'll put this YouTube video up. No problem. No problem, everyone. Thanks for coming. Thanks for entertaining me, or at least listening to me back ramble.